This video is going to go over how to solve a couple of different types of calorimetry problems. And so the two problems we have are shown here. So the first one we'll start with, where a 0.5 gram sample of potassium chloride is added to 50 grams of water in a calorimeter, and the temperature is found to decrease by 1.05 degrees Celsius. What is the approximate amount of heat involved in the dissolution of KCl, assuming the specific heat of the resulting solution is 4.18 joules per gram per degree Celsius? And then, is this reaction endo or exothermic? So we have a couple things we need to think about here. We could start, if we want to think about what the process of going on is, writing a chemical reaction. What we're looking at is KCl solid going to potassium ions aqueous plus chloride ions aqueous. So this is the problem that we're looking at. We're dissolving 0.5 grams of the KCl. And then when we do that in 50 grams of water, we find that the temperature decreases by 1.05 degrees Celsius. Ultimately, what the question is asking for, if we tease this out, is what is the approximate amount of heat involved? So we're looking for heat, and so we can think about we're solving for Q. Now, we need to remember a couple things with our coffee cup calorimeter, and one of the things to remember is what we want is Q of the reaction. So what is the heat involved in the dissolution of KCl? But in a calorimeter, what we measure is the solution, right? The water that's in that calorimeter. So we have to remember this relationship, that the heat of the reaction, right, is going to be the same in magnitude to the heat flow of the surroundings, but opposite in direction. So to represent that, I'm going to show that the heat of the reaction being a negative value and the heat of the surroundings being a positive value. Right? We might find out that's the opposite, but the key thing is they're opposite in directions. Heat is lost from one thing and it goes to the other. So what we're going to start off doing then is solving for the heat of the surroundings. And we can do that using our Q of the surroundings equals mc delta T, right? And now we can start to plug in our values. So we know that M, and so this is the mass of the surroundings, so that's the water, so 50.0 grams of water. We know, this is Q of surroundings, that the heat capacity of the water is 4.18 joules per gram degrees Celsius. And then last is we have to put in our change in temperature. And here, the change in temperature is given to us directly. We're told it decreases by 1.05 degrees Celsius. So that's going to be a negative 1.05 degrees Celsius. We can look at our units and see grams cross off with grams, degrees Celsius cross off with degrees Celsius. So we're going to be left with joules. So you can go ahead and punch that into your calculator, and we should find that Q of the surroundings is equal to negative 219 joules. Now we need to be careful when we think about this, because the question is asking about the heat of reaction. So this is where we have to go back and remember that the heat of reaction is opposite in sign but equal in magnitude to that of the surroundings. So the heat of our reaction is equal to a positive 219 joules. And that positive number means that it is an endothermic reaction. And that should make sense, I hope, if we think about it in terms of the temperature went down. So because our temperature change decreased, That's telling us it's an endothermic because the water had to give heat to the reaction for that reaction to occur. So our final answer is 219 joules of energy was absorbed, making this an endothermic reaction. So the second question we want to look at has to do with identifying an unknown metal, or really identifying the heat capacity of an unknown metal. And so here we're told that we're going to place 25 grams of an unknown metal at 100 degrees in a coffee cup calorimeter. And now we're going to measure the temperature change of that solution. And from that, we have to determine the specific heat of the substance. And we can use that specific heat to then identify the substance. Just like before, it's good to write down a couple things to remind ourselves. Remember that what we're going to measure is the heat flow of the water, but what we need in the final answer is the heat flow of the metal. So we, again, just like in our previous problem, we can write the heat of the metal is going to be equal in magnitude but opposite of sign of the heat flow of our surroundings. So the heat flow of our metal is equal to the negative heat flow of our surroundings. So we can start off and calculate, let's find the heat flow of the surroundings. And so when we think about the surroundings, and if it's helpful to sort of organize our thoughts here with our surroundings, we can notice a couple things. We know the mass of the surroundings. That's going to be the mass of water. That's 50.0 grams. The heat capacity of our surroundings, right? So that's going to be, we're dealing with a water solution, so 4.18 joules per gram per degree Celsius. So we got that either from the previous problem or from looking it up. And then the delta T of the surroundings, right? So that's going to be the final temperature of the surroundings minus the initial temperature of the surroundings. So that delta T, if we plug in our numbers, is going to be the final temperature is 27.1 degrees Celsius minus our initial temperature of the water was 19.3 degrees Celsius, which ends up, we can calculate that out. So 27.1 minus 19.3, and we get 7.8 degrees Celsius. So now we can go ahead and plug that in, and our Q of the surroundings, always good to keep it labeled, is now going to be 50 grams of the water times the 4.18 joules per gram per degree Celsius times 7.8 degrees Celsius, and Q of the surroundings is then equal to 1,630 joules. So that's really the first step of this problem, right? So now we have to go back to our relationship. Up here, where we know the heat flow of the metal is equal in magnitude and opposite in sign. And so now, once we have this value, we can come in and say the Q of the metal, the heat flow to or from the metal, is going to be negative 1630 joules. Right? So it's same magnitude but opposite sign. And now we can go ahead and say the mass of the metal from the problem we can look at was 25.0 grams. The heat capacity of the metal is our unknown. That's what we're trying to find. And the delta T of the metal then, again, we have to do final temperature minus initial. So the final temperature is 27.1 because everything's going to end up at the same temperature. And the initial temperature was 100 degrees Celsius. So now we can go ahead and plug this in. And we're going to say we're solving for that heat capacity. So we can rearrange our equation. So our equation is Q equals mc delta T of the metal. We're solving for C. So C is equal to Q over m delta T, which now we can plug in. We know Q is negative 1630 joules. We know M is 25.0 grams. And we know that the change in temperature for this is, and I don't think we calculated that, so let's go back and calculate that, negative 72.9 degrees Celsius. So negative 72.9 degrees Celsius. Notice the two negative signs will cancel out, and that should happen because the specific heat has to be a positive number. So our final specific heat is 0.894 joules per gram times degree Celsius. And if we look that up on the table, we could find out that that is most likely aluminum. Thank you.